So, what is a fractal? Well, a fractal is defined as an infinitely complex pattern that is self-similar across different scales, which sounds complicated, but it's actually quite simple. So the infinitely complex part just means that if you zoom in on the pattern forever, then the same shapes will just continue to appear over and over again. Self-similar means that the pattern just repeats itself at different scales, and that different scales part just refers to the size it's being displayed at. It's basically like the scale window and scalar the window tab on our graphing calculators. So this basically just means that a fractal is a pattern that repeats itself forever at all sizes. They're often linked to and driven by recursion, which means they apply smaller versions of themselves over and over. Basically the definition. And however, fractals are actually quite easy to make, as you just need to repeat the same process over and over again on one pattern or shape. So there are three main types of fractals: those that appear in nature, those that appear in geometry, and those that appear in algebra. Nature has made use of fractals for billions of years, and you've probably noticed them before. Most of them don't tend to be infinite for obvious reasons, so here are a couple examples from nature. Next up is geometric fractals, which utilize basic geometric shapes and can be among the easiest to model. A good easy example of this is called Sierpinski's triangle, which is created by removing the middle triangle from each triangle in each generation of the fractal. Another good example is called Cook's triangle, or snowflake, or curve, depending what you're doing it on. This is where you place the middle third of a line segment with two lines that form an open triangle. And so the more generations that this fractal has, the longer its length actually becomes as you zoom in, because you see more and more parts of the fractal, which you can measure. When you apply this fractal pattern with a triangle as the base, you get the fractal shape known as Cook's triangle or Cook's snowflake, which come from either the base shape of the fractal or what it looks like when it's fully developed. Lastly, we have algebraic fractals, which mainly came around from the rise of computers because their difficulty graphing them otherwise. And they work by calculating a simple equation over and over. So one of the earliest discovered was the Mandelbrot set, which is z new is equal to z old squared plus c. And on the Mandelbrot set, the black represents points inside the set, while all the values of c that cause it to go to infinity are on the outside, when the colors on the outside are proportional to the speed at which they expand. And quite obviously, different equations will make different algebraic fractals. Well, the concepts for fractals were around before Mandelbrot defined them in 1975. They were so hard to comprehend that Mandelbrot only did it because of the rise of computers. He started his investigation into fractals in nature because of how prevalent they are there, which can be seen in his report on the so-called coastline paradox, which is basically summarized that if you try to measure the length of a coastline, it will vary depending on the size of the tool you measure it with. The smaller the tool, the more accurate your results. But this means that with an infinitely small tool, the length of the coastline is infinitely long. So, in the 17th century, a man called Gottfried Leibniz pondered self-similar recursiveness in geometry, sounds similar, but thought that only a straight line could be demonstrated with this. He described this with the term fractional exponents. Then in the 18th century, Jean Perrin and William Fellers discussed Brownian motion, which is a natural phenomenon which is chaotic in nature. Again, sound familiar. Then throughout the early 1900s, several mathematicians, including Koch, Sierpinski, Fatou, Julia, and Levy, all described new types of geometric fractals, and then Hausendorff contributed to the definition of fractals. Due to their nature of being self-repeating, they often represent dynamic systems. These are systems which describe the time dependence of a point in its space. Examples of dynamic systems include populations, economies, and even epidemics, all of which can be modeled through fractals. So in short, fractals are generally tied to represent so-called chaos, which is actually very organized and follows patterns. By studying chaos through fractals, some people try to predict patterns in dynamic systems that otherwise seem unpredictable. So, due to their closeness with chaos in nature, a wide use for fractals is analysis and modeling. So this allows for the prediction analysis of various things throughout nature, which include cloud formations, animal migration, weather forecasts, water currents, soil erosion, and seismic patterns. There's actually a ongoing theory in astronomy that our entire universe is fractal at all scales, which is currently unproven because they need more data. Fractals are also used in fluid mechanics to analyze chaotic and complex turbulent flows that are difficult for them to model. Doctors have also used fractal analysis to judge the health of blood vessels and lungs as well, because those follow fractals. Finally, they're also used in fractal image compression in computers and to model the roughness of a surface. In more physical uses beyond modeling analysis, there are new types of antennas that have fractal shapes, and they're being used more often because they have a more compact shape, yet can pick up better signals. There's also cooling chips in various electronics and computers that use fractal geometry to channel coolant across its systems. And finally, fractal-shaped space-filling devices are used in fluid mixing for mixing without much turbulent stirring. The term fractal actually comes from the Latin term fractus, which means broken or fractured. And this video, it's been playing on screen right now, is actually what happens if you zoom in infinitely on the Mandelbrot set.